So the topic which I'm going to cover today is Introduction to Advanced Robotics in an Industry 4.0 setting. So during this presentation, this is what we are going to see. So first we'll be seeing what is a robot. I'm sure many of you might be knowing it already, but still. After that, we are going to see a short, brief history of robotics. Then we'll look at certain fundamental aspects of industrial robotics. Then we are going to see a carousel of few industrial and service robots. And I'm sure all of us are going to enjoy this aspect. So this carousel is nothing but we are just going to see a list of robots that are available now in the world, as we speak, and which are in action in an Industry 4.0 setting. After that, I'll be giving you a short software demo. We'll be using the software MATLAB. Then we'll be discussing on few novelties in robotics, the future of robotics, a little bit of brainstorming if time permits. And in the end, I'm going to conclude by discussing about the current statistics in robotics field and how it's going to affect the career path and job opportunities. So let's start with what is a robot. Now, if you look at the Oxford Dictionary for robot, so it says that it is a machine resembling a human being and it is able to replicate certain human movements and functions automatically. And there is also another statement, a machine capable of carrying out a complex series of actions automatically, especially one programmable by a computer. So this is the definition which is there in Oxford Dictionary. And now if you look at another authority in robotics, which is Robot Institute of America. Now, if you take lots of robot textbooks, this is the first definition which you will find. I'm sure many of you might have come across this in your bachelor's degree or in your master's degree. So it is nothing but an industrial robot, is nothing but a reprogrammable, multifunctional manipulator designed to move. First let's complete, then we'll just break it down into parts. It's designed to move materials, parts, tools, or specialized devices through variable programmed motions for the performance of a variety of tasks. So now if you look at all of this, there is one term which is getting repeated, like programmed and automation. So that is the very essence of robotics. So we are trying to do something which was once upon a time done by a human being, and we want it to be done automatically without human intervention. Though we have achieved automation in most of the aspects, we still have certain human intervention here and there, all for a good cause, for good reason, which we'll be understanding at least by the end of this presentation. But if you look at the general definition, so it is programmable. It needs to be programmable. That is, the human being is the one who is going to program, at least till now. But with the emergence of machine learning and artificial intelligence, even that's changing nowadays. And it's going to be multifunctional. A robot must be able to do multiple tasks. But all this is debatable because now if you go to a shop floor, you can see a welding robot, right? So you can say that that robot is going to be doing welding all his life. But there's another person who can debate that if he changes the program for that robotic arm, it can become an assembly robot or something else, right? So it's multifunctional. It should be multifunctional as per the definition by RIA. And it must also have the ability to move some material or parts or some specialized devices for performing a lot of variety of tasks. So now after we've seen the definition, now just let's ask ourselves a question. So what will a robot look like? Now, if you look at this slide, so you can see there is a very familiar picture, that orange color robotic arm, right? So that's the picture which most of us might have seen in the shop floor. So that's a robotic arm. Then you can see it's a space robot, astronaut. It's a robot which does the task of an astronaut. And the next picture, it looks like a toy actually, which you can gift to your 1-year-old, 2-year-old. But you'll be amazed to know that that is a robot which is being used for a rehabilitation purpose. So this is a robot being used in old age homes where the people who are suffering from Alzheimer's disease and all that, they're able to get back to their normal life with the help of that robot. And then the next you have ABB Yumi. So we are going to be seeing the simulation of that this robot. That is the fourth robot in the first line. Then the next one you can see. So I can just go on. But the point is, if you look at here, a robot can look like anything. Okay, it can look like a human being, which then in that case we're going to call that as a humanoid robot, or it could be look like a quadcopter. You can see the last one in the second line. I'm sure most of us might have seen this now. We can go to even a wedding function. We can see this quadcopter hovering over us, capturing the moment in various angles. And you can see the last line, you can see something like a car. Okay, you can say that that's not a robot, but even that can be considered as a robot. It's just that it's looking like a car. That's it. So if you look at Waymo Robotics, which is the company that originated out of Google autonomous driving system, I'm sure it was in the news and all of you are familiar with it. So we have now robots, cars, which can drive in automation mode. So you don't have to drive it. You can just switch on something and it automatically takes over. The steering, braking, everything is taken over automatically. So that also satisfies the definition which we saw in the previous slide. And the last one, you can see it's lifting a person. It's like a wheelchair. So The point is, a robot at present can look like anything, or sometimes it need not have a physical body. Okay, so it can even be a software, right? So you can even call your, Siri or Alexa also robot. Okay, it can be called as a, chatbot or a voice bot. So we have a bot suffix to it because it is also called as a robot. So a robot could be a software, a hardware. It can look like anything. Okay, so that's the point which we're trying to make through this slide. Now, when we look at the world around us, so these are the robots which we have at present in our world. So these are all real robots. So how do we came to all those designs? Of course, nature is always the best teacher. So man learned from nature when he's making most of these robots. So there's inspiration everywhere you see. Okay, so you have an elephant, and man has come up with the elephant trunk robot. We'll be seeing one of the slides, and you have a bird, and Festo is a company which has come up with a smart bird, okay, which can flap and it can move just like a. There is a very famous TED talk. Some of you might have seen it, and you have the cheetah. So there is a robot. So all the animals which you're seeing now, there is a robot exactly like this. Okay, the thirst for learning from nature and trying to replicate it in actual engineering domain has pushed the boundaries of technology so much that many new technologies have come up. Now, if you see the last one, there's something called swarm intelligence, right? So a group of, and even the birds also, you can see how the birds are able to navigate from one place to another, right? How they're able to migrate in such a formation. If you just go into the dynamics of all that, it's going to be very, very interesting. If time permits, we can discuss at the end of the session. And so whatever picture you're seeing here, there's a robot which is inspired from this, okay? So the inspiration from nature, we call it as biomimetics. Now, this is a very good essential lesson for any person who wants to involve himself in robotics. So even if you want to be the one who want to be a robotics engineer or a roboticist is the short form for a robotic scientist. Okay, if you want to become a roboticist, then this is where you take your nature inspiration from. Okay, you take inspiration from nature, from around you, and also within you. Okay, you can look at the heading. It says world around us and us, because the robotic arm which you see in the industry, it's nothing but a dumbed down version, a dumbed down copy of your own your own arm. Your arm is the most sophisticated arm, and compared to your arm, the industrial arm which you can see in the companies like Hyundai or Ford, wherever, whichever shop floor you go, that is nothing when compared to the technology that is there in your own arm. Learning about the biomechanics of your body, that is also a starting point for learning about robots, because inspiration is very, very important, especially for learning a high technology like robotics, because it's the inspiration that's going to take you far more into the depths of this technology. Without that inspiration, most of us might get very tired, or the technology might be very daunting when we look at it, and just when we think that, okay, how am I going to learn all this, that's going to make you very tired even before you start. So that's where the inspiration comes. So the main objective of this slide is just to show you that we get our inspiration from nature, and everybody likes nature, right? Who doesn't like nature? We all like to have that walk in the nature, the beach, and just have a look at the animals and all that. And you'll be surprised to see that's where the philosophy of robotics and automation stems from. So this is a slide where you just think, so what is this philosophy, right? So automation has been there. The idea of automation has been there for a very, very long time. Right from the mythology. If you look at the Greek mythology, automaton is nothing but they are not living, they are non-living, they are machines. It's an army of machines which comes and attacks. And if you can damage them, but they can go back and they can once again repair themselves and they can come back. And if you even take our own mythology, like the Vimana, Pushpaka Vimana, which could nothing but autonomous flight. So our inspiration is from the mythology, because mythology shows that man has always wanted automation. There is a saying that necessity is the mother of invention, and there is another saying that laziness is the mother of invention. So whatever which is the truth, man wanted something to be done automated. There were some tasks which man did not want to do. Maybe it was boring, maybe it was dangerous, maybe it was very difficult for him. Whatever be the reason, so he wanted some things to be automated, right? And that's where robotics came in. And we have software, right? Software also automates some of our mental activities, some of our tasks which we do, right? Most of us might be subject to some company exposure. So you know that once upon a time, 10 or 2 decades back, man used to do everything. Now you have some macro which does the same activity just in a fraction of a second, right? So even software does automation. Now, how does robotics link with automation? So robotics, especially the physical robots, okay, they are the ones which truly impact the surrounding. Even our robot has a software as its algorithm, which is running in its robot brain. But our robotics, it also has its physical, end effectors, as we call it, our robotic arms, which can interact with the environment, in multiple modalities, and it can get a lot of tasks done. So through robotics, we reach a wider range of sensors and wider range of actuation when it comes to our physical world. So as this heading has Industry 4.0, I'm sure all of you have seen this, I'm sure. Okay, because this is not your first webinar. So if you definitely had some other high technology, there must have been a slide with this. I can even bet on it. I'm sure you have seen it. So I'll go slide to the last one. There is Industry 4.0. So you can see cyber physical system. So that's where the robotics comes in. And Internet of Things, that is also a subfield of robotics. See, robotics is a highly multidisciplinary field. You take any field and I can link that field with robotics. On the outset, that field might look like something which is completely that is away from robotics. But trust me, directly or indirectly, if you just spend a little bit of time, you can definitely link that with robotics. For example, if you're an English teacher, you've been an English teacher all your life, even you have a role in robotics. Okay, how can an English teacher teach robotics? Maybe an engineer, okay, but how come an English teacher? Okay, you can ask that question. But if you want your robot to be something which, a robot like an Alexa, I can bet on that Alexa had some linguists working behind Alexa, which is trying to understand any accent, right? So my accent or your accent, Alexa has to understand, it has to respond. Okay, and it has to, there's something on natural language processing, which is very famous now. Okay, people have a lot of machine learning algorithms to do natural language processing. So this natural language processing algorithm can be implemented in my robotics. The algorithms for natural language processing was created based on the expert experience of an English teacher or a person who is working on the phonetics of English, right? So this is just one example. You can take any person and you can link with robotics. So robotics it has a highly multidisciplinary, and its range is huge. Now we are going to the history. So let's start from who coined the term robot. So robot is coined by playwright Karl Capek. So he's a playwright. He did a play called Rossum's Universal Robots. In this play, the first time the word robot was used. The meaning for the word robot is worker or servant or forced labor. And after that, we have our next superstar of robotics, Isaac Asimov. I'm sure many of you have heard about it. So he has written many science fiction stories. So where he has framed the framework of the present day social robotics and even other aspects of robotics. So I'm sure you might have seen a movie called iRobot. So where there is a detailed discussion and a detailed interesting scenario of these 3 laws of robotics. So I'm not going in depth into that. And now talking about the industrial robotics. So the first industrial robot was a robotic arm, otherwise called as a manipulator. Now what you're seeing here, okay? So you're seeing the fathers of industrial robotics. That is George Devol and Joseph Engelberger. So they are the people who came up with first robotic arm. So they made a company called Unimate. So Unimate made a robot called Puma. Puma is the famous robot. Even now it is there. I mean, if you open any robot simulator, you'll definitely find Unimate. That is Puma as one of the simulator in it. So this is the first patent which was published. This is the first patent under robotics. That is under the title Programmed Article Transfer by George Devol. Even at that time, you can see that there is a little bit of, you can see the truck had a mounted crane, okay, which is hydraulically actuated. And the next you can see you have that Fanuc S500 robot, which is performing, sealing on a truck. That is in an industrial assembly line. Even Ford is also another company which made intensive use of, this robot, Unimate robot. In fact, the picture which you're seeing in the second line, that is second picture, second line, there is nothing but a Ford assembly line. So Ford, they invented the assembly line, and in their assembly line, they had these robots. So this is how it started. But now we have a variety of manipulators. So what we're going to do in this presentation is we're going to have a look at the fundamentals of industrial robotics. Then after that, we're going to be seeing in the other forms of robotics, so you can appreciate the, how we starting from these kinds of robots. Okay, how now we evolved into all those latest types of robots. Okay, a robot on top of a mobile platform, on a legged platform. Okay, in the coming carousel, you'll be able to appreciate all. So manipulator is nothing but a kinematic mechanism. Okay, it is nothing but a series of links which is connected by a joint. So here in this picture, you can see the one that is at the bottom, that is link 0. That is nothing but your base. Mostly it is fixed. Okay, so what you're seeing here, it is nothing but a serial link manipulator. Why I'm going to call it as a serial link manipulator? Because I have a series of links. So you have link 1, link 0, link 1, link 2, link 3, etc. And what connects link 0 to link 1? That is joint 1. And what connects link 1 to link 2? That is joint 2. Okay, so this industrial arm is very analogous to our own arm. Okay, so we have a shoulder, then we have our elbow, then we have a wrist. So shoulder, elbow, and wrist, those are our joints. And the bones that are in between these joints, those are nothing but the links. Okay, so a very good way to understand industrial robots and learn industrial robots is just to observe our own arm. Just have a look at your own arm. I'm sure most of you are watching this webinar through your mobile phone or laptops. So if you are watching through mobile phone, you are holding a mobile phone using an arm, correct? You're holding a mobile phone. No, you're adjusting a mobile phone, right? There is an interaction between your arm and your eyes. So you just observe your own activity which you're doing now. So this is a very, very high level activity which is happening in our Industry 4.0 scenario. So what is happening here is visual servoing. Okay, there's a term called visual servoing. So visual servoing and the corresponding activation of a industrial arm. So this is a very high level activity. Okay, so you can have an object that is moving in a conveyor in a high speed, and this can track that object, and it does complicated shape, of welding or some other operation in that. Okay, so it's a very high level activity, and only now we have, at least a decade back, only now we have come to this level. But we as human beings are able to do that a lot easily, and we have been doing it for a long time. So first you observe yourself, see how your arm is able to move, how you're able to look at an object and reach, what forces you are able to transfer to the robotic arm. When you're holding an egg, how much force you are transferring. Okay, when you're holding a very heavy object, how much force you're transferring. If you're going to lift a heavy egg, will you be able to lift it without breaking it? Mostly no. Thank God the eggs are very light. But let's say that egg is going to weigh some 20 kg or 30 kg. The shell is going to be of the same strength. But if it's going to be some 30 kg, just the force which you're going to apply to lift it, that force itself is going to break the egg. Am I right? So just see how many different types of objects you're able to lift, how many different types of manipulation you're able to do, and if there's going to be a pillar in between you and the object, how you're able to bypass and go to that, you're able to reach that object. Just observe your own arm. Okay, so this is an activity which anybody can do. Observe your own arm, and that is definitely directly going to help you in understanding the concepts that are behind a successful operation of a latest industrial robotic arm. Now, if you look at a robot, no, not just a robotic arm, any robot. So these are the fundamental components. So your robot needs to interact with the environment. So there's going to be sensors involved. If you want your robot to listen to sound, you need to have a sound sensor, a microphone. If you want your robot to see something, then you need to have a rudimentary light sensor, a photodiode, or maybe a high-level camera. Or if you want to have a so depending on all the physical quantities which you want your robot to sense, you need to have separate, appropriate sensors. So definitely your robots must have sensors. Okay, so we have 5 sensors, right? We have eyes, ears, nose, there is a taste and smell, right? And of course our skin, touch. So these are 5 sensors. So we can give all of this electronic counterpart to these sensors. Okay, so the smell and taste, they fall under the category called chemical sensors. Our eyes follow the category called light sensors. The ears, we have sound sensors, and touch, we have tactile sensors, we have load cell, we have many things. Then we have actuators. So after sensing, so sensing is we sense the environment. Now after sensing, I need to interact with the environment, right? I need to make a change in the environment. Maybe I want to move an object, or maybe I want to cut something. So for that I need actuators. Okay, so actuator, we have our fingers are our actuators, correct? Our muscles are our actuators. Even our bones, very bones are our actuators. Now I have the sensors, I have the actuators. Now I need to have something called as the brain, correct? So controller is nothing but your brain. Controller is for human being, our brain is our controller, correct? So we have our brain, which is capable of, doing a lot of tasks. We have various portions in our brain. Okay, we have a segment, we have a portion behind you, that is just above your neck behind, which is, that is your cerebral, optical cerebral cortex. So that's responsible for your vision, and there is a portion which is responsible for your emotions, and etc. etc. So for our robot, we can have an Arduino board, we can have a Raspberry Pi board. Okay, if you're going for a microcontroller, mostly you go for a microcontroller if it's going to be a untethered, standalone robot. And the computation capabilities are increasing, with every version that's coming up. So there's a lot of new processing, new tasks which are capable for our robot because of this increasing computation capability. So that's where the control comes in. And then, of course, we need to have our energy. So we need to eat food so that we are able to do all of these tasks. So even a robot must have something like a battery, right? So that's where the power comes in. So if you look at the industrial robotic arms, I'm just quickly run through this. So if you look at our own arm, we have a rotational, joint. That is the R, which you can see, under rotary motion. Or if you're going to have a piston cylinder arrangement, we have a translational motion. Okay, we have twisting motion, revolving motion. So these are different types of joints which are connecting our links in the robots. Okay, so we can have a variety of mechanisms for our robots depending on the application, of course. And also a robot can have different configuration. The robotic arm can have different configuration. So this you can see, this is a polar configuration. So you have 3 rotations. Okay, we have three joints, and all joints are rotational joints. Here you can see we have 1 rotation joint and we have 2 sliding joints. Okay, and this is called a cylindrical one. So you can have T is nothing but the rotation, first rotation. The L and the O, so those are your translation. Translation means you have sliding motion, and you also have all 3 sliding motions, which is nothing but you can see your overhead crane, that gantry type manipulators. All those fall under this category. And this is your famous jointed arm robot, which are found in most of the robotic arms. That is, all of them are rotational types. And if you go for companies where they assemble the electronic chips and all that, so they mostly use this Cara robot. It has 2 rotation type of joints, and the last one is a sliding translation type. And most of the industrial robots, they have 6 degrees of freedom. Okay, so here you can see all of these are 3 degrees of freedom. So degrees of freedom is nothing but each joint is going to have 1 degree of freedom. So that means that that joint has a rotation or a translation. Nowadays, some joints have even both or some like a screw type. So that's going to have more than 1 degree of freedom at a joint. But in these slides, each joint has just one degree of freedom. So 3 joints, 3 degree of freedom. And I'm going to attach this wrist also to any of these 3. So totally, I'm going to have 6 degrees of freedom. Okay. So most of the industrial robots we have now, they are all 6 degrees of freedom. So let me just give a little bit technicality. Okay. So I don't want to scare you all by giving more technical details. How do we control this robotic arm? So of course, kinematics is involved. Dynamics also is involved. So first thing you need to study when you're making industrial robot is the kinematics aspect. So each robot has something called as an arm equation, which you need to frame. Okay, which is nothing but a matrix made by multiplying a lot of rotation matrices. So you have something called as a frame. So each joint is going to have a frame, which is going to be linked to that the adjacent link. So you do some transformation from the first frame to till you reach the last frame. So the last frame is nothing but called as a tool frame. Okay, or something it's also called as tool coordinate system. And the first one, okay, which is there in the base, mostly it's called as the world coordinate system. So in between, each link is going to have its own coordinate system. So coordinate systems can also be called as a frame. There's something called kinematics. So the kinematics is of 2 types. One is called forward kinematics. Another is called as the inward kinematics. Now, if you look at this diagram, forward kinematics is where you know the joint angles. So you have joint 1, joint 2, joint 3. So let me say I'm setting joint 1 as 10 degree, joint 2 as 20 degree, and joint 3 as 30 degree. Now, if you're going to ask me what is the position of the tool, or what is the orientation of the tool, or you can just call it as the pose, tool pose, I'll be able to find it out. Okay, it's a very simple problem. Okay, it's nothing but trigonometry, sines, and cos. I'll be able to tell you there is going to be only one solution for that. So that is called forward kinematics. So I set the joint angles, then I calculate the tool. That is, the tool is the one which is at the end, at the top. Okay, that is called forward kinematics. And as the name suggests, inverse kinematics is the reverse. Mostly, I will give you the tool position and tool orientation. Okay, I will give you the tool pose. For that particular tool pose, you have to come up with the joint angles. Okay, what's going to be theta 1, what is going to be theta 2, what is going to be theta 3. Now, this is difficult. Okay, this is not as easy as the forward kinematics, because forward kinematics is going to have only one solution, but inverse kinematics is going to have multiple solutions. Because you can look at yourself, right? You're holding a mobile phone. There are multiple ways you can hold your mobile phone, okay, at the same location. You can just fix the mobile phone in space, okay, but you can move your elbow around. There's going to be n number of configuration of your own arm to position that mobile phone in space in the same fixed position. So it can be very clear that forward kinematics is going to have only one solution. That's why it's very easy to solve. But inverse kinematics is going to have multiple solutions. And we need to decide which solution suits us as per our application again. So robotics design is completely based on the application, right? It's application oriented. Is it welding? Is it going to pick and place? So first you need to start from the application, and correspondingly you need to design every aspect of your robot. So this is something which you need to remember. And this is a very famous Danavid-Hartenberg representation. So this helps us to convert the robot which you're going to see in the left to the robot which you're going to see in the right. That is, both are same. But if you look in depth, right, this is nothing but a geometric representation. Whatever you're seeing the right, left is nothing but the diagram which we just saw in the previous slides, right? So I can convert any robot into a geometric representation. And this geometric representation is going to help me to mathematically to create my arm equation. So the creation of the arm equation is called the forward kinematics. Now solving the arm equation to find the thetas, that's going to be our inverse kinematics. So DH representation, any course, if you take any course on robotics, this is where you're going to start. And end effectors are nothing but depending on the task which you're going to do. You can have a gripper, you can have a humanoid, the one which you're seeing, that's the third one at the top. Right, that's anthropomorphic. Anthropomorphic means it is resembling a human hand. So depending on what you want to do, what task you want to do, you can go to any of these end effectors. And the last one which you're going to see, it's a end effector which is created by 4D printing, which I'll be sharing in the coming slides. That is, we are using an advanced smart material to 3D print a shape. Okay, you give some stimulus to it, it changes its shape. And that is used to grasp something. We'll be discussing that in the coming slides. And of course, we need the power source. We need the muscle. So this is nothing but a muscle. You can use hydraulic cylinder or hydraulic motor. You can use pneumatic power. You can use electric power. And if you go for electric power, you have different types of motors, right? DC motor, AC motor, stepper motor, servo motor. You can use any of these. And of course, sensors we just discussed. So you have the FlexiForce sensor. Every year you have new sensors that are coming up, and the costs of sensors are going down. So a robotic person has to be aware of these sensors. He should be aware of the actuators, aware of the sensors, and aware of all the microcontrollers that are coming up. Okay, as I told you, it's a highly multidisciplinary. So your awareness of these latest boards and latest sensors is going to help you in designing a very good robot for your application. So it's your task to keep yourself updated at all times.